All right, everyone. So we are now going to be starting graph theory. This is a pretty important concept for you to grasp because it's used in a lot of questions. There's generally at least one or two of these on the CCC senior and at least one on the CCC junior usually. So it is important that you understand this. So what is a graph? Anyone have any guesses for what a graph is? We have displays data, X and Y graph. All right, so I guess I can see where you guys are coming from. So a graph is not like a bar graph or something, right? It's not like, oh, yeah, I have this and I have a population or whatever. What we're talking about, a graph, is a relationship between something. So we're mapping out the relationships. So the definition of a graph is a collection of vertices, which we will call V, and a collection of edges, which we will call E. All right. And the edges consist of pairs of vertices. So what you can do is you can kind of think of vertices as locations, right? So you have like location 1, location 2, location 3, location 4, or whatever. Those are your vertices. That's your set of vertices. And then after, the edges would represent like a road or a path to a vertice. So then after, your set of E edges would essentially be all the paths that connect the locations. So a graph doesn't necessarily, so in a graph, right, you don't need a path to every single node, between every single node, right? All our edges are just potential paths that are being described. So for example, when we do draw these out, we'll generally use circles for our vertices, and then we use lines for our paths or our edges. So in this case, we're going to be using this graph. This is a very nice graph. It demonstrates quite a few properties. So this is actually available on our lesson plan that I'll post later. All right, so this is our little simple graph, okay? So in this case, we're just going to say that, let's say this is vertice 1. All right, this is going to be vertice 6. This is going to be 5. This is 2. This is 4. This is 3. So in this case, our vertices are going to be 1, 2, 3, 4, 5, and 6. All right. And then our edges is going to be 1, 3. Then we have 1, 6, which is the one between 1 and 6 here. Then we have 2, 5, which is the one between here. Then we have 3, 4. And we have 3, 6. Sometimes instead of calling these vertexes, we're just going to call them a node. All right. Nodes on a graph, but those two are interchangeable. So if you see that on a question, they're just talking about a vertex. All right. And then after, just note that if there is a vertex here that is just alone with no edges connecting it, we're going to call this vertex isolated. So this is an isolated place. So this might be a place that has no points or paths, a place that doesn't have any way to get to it. This can be a value that's impossible to get, whatever, right? That just means it's isolated. Okay, and another thing that we can have here are numbers on our edges. So these would represent weights. What this would kind of implies is the cost of going through this location. So for example, if we were to have a mapping app and we're going to say that the distance between 1 and 3 is smaller than that of 1 and 6, what we can say is that we can have this edge has a weight of 1, while this edge 1, 6 has a weight of 3. So this describes how much effort it takes to get from these two vertices. So this is weighted. These are weighted edges. All right. And it's a very similar concept for weighted vertices. A few more definitions. So we're going to call an edge a self loop if its format. So for example, right, remember that we described the edges based on the two vertices that it connects. So for example, this edge right here is going to be 1, 6, right? So if our edge is described as u comma u, which means it has the two same numbers. Thus, it kind of does this, right? It loops back on a vertex. This is going to be called a self loop. All right, in this example, here, if we're going to just delete this, right, our graph has no self loops. Okay. Now, if a graph does not have any self loops, and it doesn't have a repeated edge, then we're going to call this graph a simple graph. All right. If we have like a duplicated edge, or we have a self loop, this is called a multi-graph. Now, we're going to be dealing basically exclusively with simple graphs, so you don't really need to worry about multi-graphs yet. So again, these are just definitions. So just make sure that the definitions make sense. You don't need to know them yet. You'll just, as you work with graphs, you'll just kind of pick them up. Next up, a few more. Sorry, guys. There are just quite a few definitions here. So next is, for example, if we have this edge that connects two of these vertices, what we are saying is that this edge is incident to these vertices. So if we have an edge 1, 6 again, we can say that this edge right here is incident to vertex 1 and 6. And now we can also describe the degree of a vertex. So this is the number of edges that are incident to it. So for example, vertex 3 here has degree 3 because we can have, right, we have 1, 2, 3 edges that connect to it. Well, vertex 4 over here has degree 1 because there's only one edge. Next, if there is a edge connecting two vertexes or vertices, we say that these vertices are adjacent. All right, so these two are adjacent. However, 1 and 4 are not adjacent. It's just if there is some edge that connects them that both of them are incident to. Okay, so those are undirected graphs. Okay, so what we're talking about so far are undirected graphs. So that means that we can go both ways. So we can put, so if there's a vertex, if there's an edge between 1 and 6, it's implied that we can go from 1 to 6 and from 6 to 1. Now, if there is a direction, so if we say, okay, you can only go from 1 to 6, you can't go backwards, what this would be an example of a directed graph. All right, so let's just put arrows. So in this case, instead of calling them edges, we're going to call them arcs. All right, so as you can see here, right, these two arcs are equivalent to just one edge in an undirected graph, right? Because there's one going in and one going out. Now, to describe the connectiveness of a vertex, we can use two factors. An out degree is the number of arcs that begin at that vertex. So basically, the number of arcs that start there, right? So we're just going to count all the non-arrows. So there, for example, for vertex 3, we have 1, 2, 3. So that's an out degree of 3. However, our in degree, which is going to be the number of arcs that terminate there, is going to be just 1 because there's one arrowhead pointing into that vertex. All right, and also, like if we take vertex 6, we have an in degree of 2 because there are 2 arrowheads, while there's an out degree of 1 because there's only one arc that's going out from it. All right. However, you don't need to worry about this. All right, if it's not specifically stated or implied that it is a directed graph, you can just safely assume that it's undirected. So unless it says, okay, you can only go one direction, or it says this is a directed graph, you can safely assume that it is undirected. All right, let's work on representing these graphs. Okay, so obviously, whenever we're solving a problem, right, we can't give the judge a drawing of the graph, right? And Python doesn't recognize a drawing of the graph. So how do we actually represent these graphs, right? So the way we do these is by defining the relationships again, right? So we're just defining the relationship between the vertices, and If there's a relationship there, there'll be an edge. If there's no relationship, there won't be an edge, right? So let's go ahead and fire up Python. And let's demonstrate how we can represent this graph. So for now, we're going to be working just with undirected graphs. So let's just do a very simple graph to start off with. Now, the first way we can represent these is through an edge list. So this is just a list of all the edges that are in the graph. So for this graph here, what an edge list is just a list of edges. So this is kind of how it would go. So we'd have just kind of a table. So we're going to represent this 2D list. It'll be a 2D list. We're going to represent it as a table for now. This will be the vertex that it starts off. We're going to call it V1 and V2. So this will be a list of length 2, right? So this part right here. And then after, these are going to be our edges. So we're going to say E1, E2, whatever. These numbers don't really matter that much. E4, 5. Okay. We can say, okay, well, the first edge is going to be 4, 3. So it starts at 4. And there. Next one, we can say 1, 3. All right. And then the next one will be 2, 5, let's say. All right. Then we have 6, 1 over here. And then after we'll have 3, 6. All right, so we're just defining, okay, so this edge contains these two vertices, and yeah. So this representation is pretty easy to code. It's also really easy to debug because it's a pretty simple like structure, and it's pretty memory efficient. However, determining the edges that are incident to a given vertex is pretty expensive. And you also if you're determining whether two vertices are adjacent, you need to go through you need to go through every single one of them and check if one of them are adjacent. All right. You can add an edge pretty quickly, but deleting one is pretty difficult because you don't know where it is in the list, right? Now, if you wanted to make your graph weighted, you just add another number. Over here, you just be, okay, the edge is weight, right? Just over here. So it's pretty easy. And then you can also represent multigraphs pretty easy as well, right? You just add another entry here. So in Python, what this would look like is you'd have a list here. It would say graph. Let's just call it G. So remember 2D lists, right? So this is going to be the number of rows. And then for each row, we're going to say, okay, this is going to be edge 1. And edge 1 we said is 4, 3. Right? And then edge 2 is going to be 1, 3. Then edge 3 is going to be 2, 5, 6, 1, 3, 6, and 3, and that's it. All right, so does this make sense? This is a very simple. Okay, so now, but you can see, right, if we wanted to determine whether vertices 3 and 6 were adjacent, we need to go through this whole list and find if there's 3, 6 or 6, 3. That is a downside, but it's pretty space efficient and it's really easy for you to see, right? You can easily see which vertices are adjacent. So a second way of doing this is using an adjacency matrix. So an adjacency matrix essentially is a way of doing it where you have a 2D list, and then after it's n by n, which is n being the number of vertices. And then what you'd say is, for example, if you say list at I at j, if that entry is a 1, what that means is that there is an edge that connects the vertices I, j. If it's a 0, then it doesn't exist in the graph. So this is taken from the lesson plan. So this would be an example of an adjacency matrix. So as you can see, right, if we pull up Paint here, if we have vertex 1, 3, we have vertex, okay, 1 is here, 3 is here. Well, there's a 1. So that means that there is a an edge connecting there, right? If we were to say, okay, 3 comma 1, that also exists right here. But if we were to say like 2 comma 2, well, there is no edge there, so it does a 0. This is not very space efficient or memory efficient. And it's really, really inefficient for sparse graphs, right? Because you don't have them in your relationships. And it's debugging is a little harder, especially if you have really large amounts of edges, because again, it's huge. So you need to go through every single one. But checking if 2 vertices are adjacent is really quick, right? All you do is just a constant. You literally just say, okay, ij, is there a 1 there? If there is, then they're adjacent. But if you find all the edges incident to a given vertex, then that's pretty expensive because you need to go through the whole matrix to find it. And adding or removing edges is also pretty expensive because you'll need to rejiggle things around. Now, if you're to make this weighted, you can simply just put a weight here instead. So instead of putting 1, we can say like 6. If you want to make this a multigraph and it's unweighted, you can just say I comma j is going to be the number of vertices that connect that. However, you want a weighted multigraph, then it's pretty hard to use an adjacency matrix. You need like a 3D list essentially. The way we can implement it in this Python is pretty simple, right? We just have this many rows. So we have, I believe we have 6 vertices. Right, and we can just say, okay, every single vertex here. All right, so this is the first row, so this will be vertex 1. We have 0, and we have 0, right? There's no connection to 2. There's a connection to 3. There's no connection to 4. There's no connection to 5. There's a connection to 6, right? And also do note that if it is an undirected graph, your matrix is going to be symmetrical, right? Because there's going to be a connection from both vertex ij and ji. This will be an example of that. And then after, if we wanted to check if some vertex was there's an edge there, we can just simply say g at, so let's check if 1 comma 3 is there a path there. Well, we'd have 0 comma 2, right? And sorry, g at 0 at 2. We can see it's a 1, which means that there is a vertex, an edge there, meaning there is a path. This is a pretty good implementation if you're not adding or removing any vertices and you're just checking if there is a path to get somewhere. This is a really good method of doing that. And the very last type is an adjacency list. So what this is we keep track of all the edges that are incident to a given vertex. What we essentially say is, okay, vertex 1, what vertexes are adjacent to it? Okay, so we just have a 2D list that contains that. So for example, in our example here, if we were to use an adjacency list, what we'd say is we'd have, okay, vertex 1. So vertex 1 here, well, we have, right, 3 commas 3 and 6 are next to it. 2, we have 5. 3, we have 6, 4, and 1. 4, we have 3. 5, we have 2. And 6, we have 3 and 1. This representation is a bit more difficult to code, especially if the number of edges. So if you're moving on to Java or C++, you're going to, if you don't have a bound for the number of edges that are incident to each vertex, you're going to have to use a vector or something. So you will need to, for the most efficient implementation, you do need to know the maximum amount of vertexes that can be incident to a vertex. And debugging is a little more difficult because you just you need to follow through with every single vertex. So you need to track it down basically. But the memory usage is about the same. And finding the vertices, so the whole list of vertices that are adjacent to another vertex is pretty cheap. But if you're checking if 2 vertices are adjacent, you need to check all the edges adjacent to one of the vertices, right? So that's a little more inefficient. But if you add an edge, it's pretty easy to add. But deleting an edge is also difficult because you need to, if you don't know the location of the edge in every single list, then you got to go through the whole thing, right? Then if you were to want to make this weighted, all you need to do is add another thing. So you maintain the weight along with this. And multigraphs are, again, pretty easy. You just add another number here if there's to be a number, another vertex here. And directed graphs are also pretty easy to handle because you just don't do one entry here, right? Yeah, so this is, again, a very common method of doing it. To do it in Python, we can simply do this. We can say G equals, so this is vertex 1. Well, it can go to vertex 3 and 6. What I would recommend is for you to start this at 0. So vertex 1 would be 0 instead of 1. So then what you can do is in our code, you can directly use the number you get, especially if you're trying to follow a path. If you can directly use the number you get out of it to address another part of your list. So in this case, vertices 3 and 6 would become 2 and 5. Then for 2, we just have vertex 4. Then after for 3, we have 6, 3, and 0. Sorry, 6, 3, and 1. 6, 4, and 1. And then after for number 4, we have just a 3. And then for 5, we just have a 1. And then for number 6, we have a 3 and a 1 here. So now we can just easily do that, right? We can just say, okay, well, G at, let's say, vertex 1, that gives us vertices 3 and 4. So now we can iterate through that and see whether we have a connection to some other vertex. And a last type thing that's pretty common is an implicit representation. If there's a way for you to imply a graph without actually storing the whole graph, usually it's a lot more efficient. So, for example, if you're trying to determine a path, if you can just store already, hey, how many paths come here, where I can go, and you don't need to store the whole graph, that is going to be more efficient, right? So you should always try to do that. But again, with the time constraints, sometimes you might panic. That's totally fine. And generally, you will be within the memory limits. All right, there's a bit more information about implicit representation and all of the other representations in the lesson plan. So be sure to check them out. I just don't want to babble on for too long for every single one of these. So there are also a few more examples of more specialized graphs and talk about connectivity in our lesson plan. However, I'm already 4 minutes over, so I'm going to skip those for now. All right, thanks again, guys, for coming, and I'll see you guys next week.